where do people usually stand on this side or on the other side?
Depends. Whether they're left-handed or right-handed, superstitious. You know, there's all sorts of weird.
So I'll just be here. It's fine. You actually got a camera. Okay, this is a good spot for me. So my head is not in the screen. Hi, I'm Selma. Good to meet you. The famous Desaf. Yes. Okay. I'm glad you were able to make it.
I was going to ask, by the way, are you available to join us for dinner at 7? We're going to go to Ganges. Okay, no problem. Sorry. Yeah, but we can do the. So we got everything lab tour after this.
Yep.
Sounds perfect.
He told me I'm on your schedule.
Hopefully doesn't fall all the way.
Yeah, not a problem.
Right, we'll go ahead and get started. I'll grab a seat.
Taggart. Just say, do you want to say Medidovic?
No, I'll say Taggart. Selma Taggart.
You can do it?
This is all being live streamed.
Taggart.
Oh, that's you.
Oh my God.
Okay.
Wow.
Okay. Hi everyone to our weekly Department Colloquium series. Professor Ivanova apologizes for not being able to be here. As some of you know, she's at a conference, I think, out in Canada. So I am happy to introduce this week's speaker. Is Professor Selma Taggart from University of Clarkson in upstate New York. Professor Taggart got her PhD in chemical engineering from Florida State University and is currently a professor in the chemical engineering department at University of Clarkson. Her specialty is plasma interaction with water and water treatment using plasmas. And with that, I'd like to welcome our speaker.
Thank you so much. So Steve told me a couple of days ago that the weather doesn't like plasma speakers, but I had no problems coming here. So I take that as a very good sign. So I'm a chemical engineer giving a talk in a nuclear engineering department. So this is going to be very, very interesting. So as Steve mentioned, really in plasmas contacting liquid. I have lots of projects going on, not only water related, but organic fuels related. But today I'm primarily focusing my talk on the plasma-based water treatment. I'm going to talk a little bit about reactor design challenges, mainly treatment of perfluoroalkyl substances and some fundamental processes occurring at the plasma-liquid interfaces. So plasmas have been really known for a long time for water treatment since the 1980s, and the early applications of plasma involved using ozone and then treating contaminated water downstream. But recently the focus has been shifted on the direct plasma treatment, which produces a very rich chemistry. You can see in a direct plasma treatment, let's say argon plasma is touching a liquid surface, or nitrogen plasma, and then this rich chemistry is being formed with this chemical reactions occurring in the plasma state. Interface brings its own set of reactions, and finally in bulk liquid, another set of reactions is occurring. So the plasma reactors, as I mentioned, for water treatment have been studied for a very, very long time, and the majority of studies so far are very scattered. Nobody really knows the guidelines for the design of good plasma reactors, but the research actually has shown, and I've done comparison of different studies, that the best plasma reactors in terms of water treatment feature these three characteristics. You need to have a gas discharge plasma contacting a liquid water, or you need to have some kind of a type of spray or a jet involving water. You have gas. You use argon or oxygen as a processing gas, not nitrogen, due to the formation of nitrates, and you're treating very thin layers of water. And some of these are the reactor configurations that fall into this category here. These are the in-liquid discharges. They are actually the most ineffective types of discharges to be formed. You have thin film reactors in which very thin films of water fall on the edges of the reactor. These are actually very good types of reactor. You have a Gleidag type discharges, as I mentioned, a very different variety of different plasma reactors for water treatment. The problem with the plasma reactor water treatment that these types of reactors cannot competitively treat different types of compounds, okay? So you have one plasma reactor that is good maybe for one type of compound, but not for the other, and so on. So in order to have very effective plasma reactor, we need to learn how to maximize the contact between the plasma and the water to be treated. And secondly, we need to eliminate any kind of mass transfer limitations from the plasma side to the liquid and from the liquid to the plasma side. And if that's solved, you're going to have the best reactor in the world. So instead of, again, building the plasma reactor and then seeing what type of compounds this reactor can treat, why don't we look at the types of compounds we are using and then build a plasma reactor around the properties of these compounds? So we really should be asking ourselves these questions before building such a plasma reactor. And you're going to see, I'm going to show in this talk how my research actually led from an accidental discovery to really a targeted plasma reactor design. So first, I'm going to talk about some plasma reactor design guidelines for water treatment that we actually discovered using targeted experiments. And then I'm going to focus on the treatment of PFAS, perfluoroalkyl substances, which are a huge environmental problem today. I'm going to present some results from the field treatment, and then end up with a plasma treatment of these PFAS-type compounds in highly electrically conductive solutions, which is a whole set of problems on its own. So around 2003, my research group received funding from EPA to develop a small-scale pilot-type plasma-based water treatment. But you know, my research group, we were wondering, okay, what is the best reactor to scale up? I just showed you, this is a very small image of the type of, like, I showed you maybe a dozen type of chemical reactors, but there are probably over 100 types of chemical reactors you can be scaling up. So the question is, what plasma reactor should we really choose to scale up? So we started actually by just using what is called point-to-plane reactor, which is just a needle in the liquid, and you have a plate a certain distance placed from that needle. You just apply 20, 30 kV potential, you form plasma, and let's start with that, okay? And we'll go further. And for these experiments, we used rhodamine B dye as a surrogate compound. It's not a compound of environmental importance, but when you're doing design optimization studies and you need to perform hundreds of or even thousands of experiments, it's very easy to analyze this compound, and we use it as a very good standard compound for the plasma reactor design. And you can see we measure the dye degradation in this reactor. You can see it's very poor. In 30 minutes, we degrade almost nothing of this dye. And you have to be degrading things in seconds if you want for your technology to be competitive. And then we just raised the high voltage needle from the liquid, and we placed it in the gas. We left the plate in the liquid, and plasma is now formed in argon gas, is spreading across the liquid, and you can see that the removal increased tremendously. It was the same reactor, just the needle position was changed from the liquid phase to the gas phase, and the removal increased tremendously. And I talked to my students, I said, okay, we need to figure out why is this gas discharge so much better than in-liquid discharge, and we will be onto something in terms of plasma reactor design. So I'm going to give you the answer to this question and actually then guide you through how we actually discovered that. So this plasma area is significantly higher than the plasma area of the in-liquid plasma. And the plasma area, not only that actually touches a larger volume of contaminated water, the plasma surface area is directly proportional to the reaction rate between the dye and the hydroxyl radical. So essentially, it makes sense, right? The larger surface area, better removal, but we need to show that. So we assume that the dye essentially degrades with only hydroxyl radicals. They're getting bleached, okay? And the concentration profile follows the pseudo first order kinetic, so the removal is directly proportional to the observable rate constant, okay? But the observable rate constant, as shown here, should be proportional to the concentration of OH radicals. We have measured the concentration of OH radicals in the liquid and compared it to that in the gas, and to our surprise, the concentration of OH radicals is much higher in the in-liquid discharge than it is in the gas discharge, even though the removal is actually poorer. So we actually had to look at the whole problem from another perspective. So what I showed you, this rate form of the equation is valid for homogeneous processes, and plasma is not a homogeneous process. So if you have actually plasmas contacting a liquid to be treated, they actually resemble a surface of a catalyst, and there's a film, there's a gas film flowing over the surface of a catalyst. So it's a typical chemical engineering problem. So we imagine that the water is the surface of a catalyst, and the plasma is essentially the gas touching the surface of the catalyst. And we actually derive the rate equation, right, for the removal of these compounds, where now the rate constant actually contains the terms for mass transfer here, which it didn't have before. So this here was the new proposed form of the rate equation with the removal rate constant is proportional to the area of the plasma touching the liquid, the volume of the liquid, then you have mass transfer coefficient, and still the pseudo first order removal rate. So the next question is, how are we going to validate this proposed rate form? So we had an idea that we can actually show just that the observable rate constant is directly proportional to the plasma area. And we decided actually to change the plasma area by changing the size of the grounded plate immersed in the liquid. So the plasma actually follows the size of the grounded plate in the liquid. So the larger the plate, the larger the plasma area. And you can really see that the plasma just radially propagates across the liquid surface. Then we call this area of the circle region plasma area. We have also done imaging studies to confirm that the degree of branching is the same for these different types of sizes of the plasma, and therefore we were able to approximate the plasma area to the interfacial area. When we plotted the removal rate constant for the dye versus the plasma area, we actually got a linear, really nice correlation indicated that indeed the removal of the compound is directly proportional to the area of the plasma contacting the liquid. So in terms of plasma reactor design, and what's important is the contact size between the plasma and the treated liquid. And if we can maximize that, we are going in the right direction. Then we have had other ideas. So now we knew actually the contact is very important. We have other ideas how to improve the contact between the plasma and the liquid. And we have actually, these are some internal names for the reactors we further develop in our system. You know, we have used the reticulated vitreous carbon type electrode, and then we are forcing the liquid to be treated to the plasma. Here is the same situation, only instead of the RVC, we just had a stainless steel tube, so the liquid to be treated directly flows to the plasma. And we measured the G50, the efficiency of the dye removal in terms of grams per kilowatt hour. And that value, the higher the value, the better the removal, increased actually, and it was the highest for what we called laminar jet with bubbling reactor, which is shown over here. So the best performing reactor essentially argon gas bubbled through the liquid. There was a diffuser, ceramic diffuser placed in the liquid. The grounded electrode was just a ring surrounding this diffuser, and the high voltage was just nickel chromium or tungsten, I don't remember anymore at this point. And the liquid was actually circulated and passed through this through the plasma zone. So the majority of the work actually we performed further from now on with this laminar jet with bubbling type of reactor. So the system worked really well on the rhodamine B dye, and the next question was, how does this system reactor actually works on a suite of chemicals? So we used random different type of chemicals, perfluoroalkyl acids, nitrosamines, some pharmaceuticals and personal care products, and haloacetic acid. We actually dumped literally this mixture of 23 compounds into a plasma reactor to see how it actually performs. And in terms of the removal rate constant of these compounds, we have actually observed that the system works really well for some compounds, as indicated by very high K value, and works really poorly for some other types of compounds, which are haloacetic acids. So my colleagues actually didn't believe that these two acids, perfluorooctanoic acid, PFOA, and PFOS, perfluorooctane sulfonic acids, were removed so fast in the reactor. They said none of the technologies can treat this compound. They're a huge environmental problem. We repeated this experiment probably 20 times. I said, okay, the result is always the same. We have to start believing that this is what's happening. And this is going to be the focus on the second part of my talk. But first, we really wanted to understand why are some compounds better degraded than others. So we looked at the chemical structures of these compounds. I won't go too much into the chemistry, but what we observed is that the compounds that have distinct hydrophilic and hydrophobic groups are really well removed, treated in the plasma reactor, but those that have only hydrophilic groups are poorly treated in the plasma reactor. And these compounds essentially resemble surfactants. Okay, surfactants tend to accumulate to the gas-liquid interfaces, and actually argon being bubbled through the liquid brings those contaminants to the gas-liquid interface where they are degraded by the plasma. So that actually made us look into how molecules are degraded by the plasma, and we have developed this so-called triple mechanism degradation scheme, where we assume that when you have chemicals in the liquid and you have plasma formed above the liquid, there are three types of reactions these molecules can undergo. Those that are very hydrophilic, they tend to linger in the liquid. They react with dissolved hydroxyl radicals primarily. Those that are semi-surfactant, they tend to go to the interface, and then they can also be degraded by either hydroxyl radicals, but also directly with the species from the plasma. But then you have very strong surfactants, such as PFOA and PFOS. And for those molecules, the hydrophobic portion is sticking into the plasma, and it's directly degraded by the species in the plasma. In this case, argon ions, metastables, electrons, whatever was present in the plasma. We have actually proven this mathematically in the paper that was published last. Based on three different types of contributions: subsurface, surface, and above surface contribution. So molecules that are very just beneath the interface, their reactivity is only with hydroxyl radicals. The removal of these compounds will only depend on how fast they react with hydroxyl radicals. Those that actually tend to go to the interface, their removal is going to depend on the KOH, the removal constant with the hydroxyl radicals, but also on the ratio of gamma to Cb. So gamma is the surface axis, the surface interfacial concentration of the compound, divided by the bulk liquid concentration of the compound. So it's essentially the surface axis. And then if you're degrading molecules by the above surface mechanism, such as here, then the contribution will depend not only on the surface to bulk liquid concentration of the compound, but also to the volume of the molecule that is actually exposed in the plasma zone. We plotted this K versus K measured versus K predicted, and actually got pretty good correlation between the two values. We have since, and still actually working on performing molecular dynamic simulations to see how molecules actually orient themselves at the interface to prove this triple mechanism model. And indeed, you can see that a PFOA at the gas-liquid interface orients itself as we predicted in our triple mechanism model. The molecules is entirely sticking into the plasma zone. And you can, sorry, the graph is a little bit low, but you can see this here is the interface somewhere region. Very large molecules, C2 to C8 portion of the molecule is essentially sticking into the plasma. So this very hydrophobic part is sticking in there. On the other hand, just an example, I show here caffeine, which is a non-surfactant. This molecule is much poorer degraded in the plasma compared to PFOA, and this molecule is just lying flat in the interface. So there will be no contribution of the gaseous reactions to the removal of these compounds, and this is why this compound is very poorly degraded by the plasma. So to answer another question of what's important in terms of plasma reactor design, it's really the chemical properties of treated compounds. You can have the best reactor in the world, but if you don't get that molecule to the interface, you will not have good performance. So I told you earlier that we were degrading these two types of compounds, PFOA and PFOS, really, really well. These compounds are a huge environmental problem, not only in the USA, just internationally, because billions of gallons of water are contaminated with this compound. It's used in for firefighting. It's a flame retardant in firefighting foams. So military training activities, they have actually resulted in contamination of groundwater with this type of compounds. Production of Teflon, anything that's stain resistant, water resistant jackets, side of the popcorn bags, they're all actually the sources of these chemicals in the water, and there are more and more studies coming out that these compounds have really adverse health effects. So this is how these molecules look like. They're very highly soluble in water. They're non-volatile, and they're surfactants, essentially. EPA has put advisory levels for the combined concentration of these compounds at 70 nanograms per liter. They cannot be oxidized, so due to the very high stability of the carbon-fluorine bond. So OH radicals, which are readily produced in our plasma systems, are ineffective for the removal of these compounds. Currently, these compounds are being just absorbed activated carbon, followed by incineration, which is hugely expensive. There's tons of funding available for the treatment of these compounds. So I have here the information that the Air Force is expecting to spend $2 billion for the cleanup of these contaminated sites. So we have actually currently funded by Air Force to demonstrate this reactor in the field. And we have actually gone from these bench scale studies that I showed you earlier to scaling up the system to, sorry, I'm using the SI units and the British units here, to 0.1 to 2 gallons per minute. It's a flow-through reactor. And essentially, the features of these reactors are the same as here. We have a saw blade electrodes. They're very pointy. You can see, and for each point, we form plasma. We have ceramic diffusers placed in the liquid, and the plates here are the grounded electrodes. So argon in this system, which is bubbled through the liquid, is never released into the environment. Argon is being recycled in the system, which actually saves energy, and we don't release any of the gaseous byproducts in the system. And this is how the plasma looks like when it's formed on a larger scale. And you can see that the focus of the reactor is really on the plasma area. You can see that we cover very large surface area of the water being treated, and the thickness is about 1 inch. So the water flows in and treated water out. So we are supposed to demonstrate this reactor in the field. It's the first example of the plasma reactor for the water treatment being actually taken from the lab into a field since the plasma water treatment reactor investigations have started in the 80s. We have packaged these 2 plasma reactors in a Faraday's cage. We produce EMI, which are actually completely eliminated once the Faraday's cage is closed. We have rotating spark gaps here and the power delivery system on the outside over here. We are going to package this plasma reactor into a trailer, into a mobile unit that is actually going to go in the field. We are currently building, an engineering company is building this trailer and actually the system inside, which is going to be completely automatic touch screen. So the system will be ready to go and be tested in the field in January. Due to confidentiality of the project, I'm not allowed to show any legends or actual concentrations. This is actual groundwater being treated here. You can see I can just allow to show normalized concentration. So it's from different sites, no pre-treatment. All the other co-contaminants are present in regulatory limits in about 2 minutes, okay, of the flow through of the water. So the untreated sample is very foamy due to the presence of surfactants, and then after 2 minutes of treatment, there is almost no foam of the present. So both PFOA and PFOS can be degraded in about 2 minutes of treatment. Lots of people ask us about the cost of the treatment. So we have calculated costs so far of the scale-up system. Cannot compare it to any other system because none of the other systems that use electricity are scaled up. So we compare it just to the granulated activated carbon here. And we are actually, even the unoptimized reactor at this point is significantly cheaper than the granulated activated carbon. I can give you more information of the treatment cost if you want later. So just to finish with this part, what is the mechanism of degradation? I would really like to know that myself. So as you know that the argon is being bubbled through the liquid and is actually attaching these surfactants to its surface, and it's being brought to the gas-liquid interface. And what's happening, the hydrophobic part is sticking into the plasma and it's reacting directly with the species present in the plasma. We know that the oxidative mechanism plays no role here. We have shown that the aqueous electrons that are present in the system, they account for about 15% of the degradation. We have shown this in a paper we published last year. The rest of the mechanism, we really don't know what's happening. The plasma, the molecules could be partially thermally degraded. We cannot decouple any of the other mechanisms. We are doing an extensive analysis of the byproducts. We are actually done. We are able to close the fluorine mass balance on the system. We know that the 60% of the starting molecule is just mineralized to fluoride ions. We have small amounts of shorter chain PFAS formed, but they also could be degraded over time. But we actually produce large quantities of short chain fluorocarbon gases, which are degraded and over time. So the problem here is we do not have standards in order to quantify what these gases are. But if you remember, we do not release our argon into the environment. So the argon, whatever gas products that are formed, they stay in the plasma. They're being recirculated and retreated over and over and over in the plasma. And at the end of the treatment, they're essentially completely gone. I want to just briefly mention some relevant research that we are doing and relates to the importance of the bulk liquid mixing to the chemical processes taking place at the gas-liquid interfaces. So at one point, we actually tried to completely turn off the argon to see how the removal actually looks like when there is no argon being bubbled through the solution. And there's actually very interesting phenomena happening in the bulk liquid when there is no external mixing. So when you have nothing present in the liquid and you just turn on your gas plasma, there's an electrohydrodynamic flow and mixing happening just due to the presence of the plasma. We are currently using particle image velocimetry to quantify the field flow in the liquid. So we just put fluorescent particles in the liquid, we shine the laser on those, we turn on the plasma and actually quantify, just collect the emissivity of the particles and calculate the velocity fields. So here what we're seeing is the gas discharge reactor, just the left side of the reactor. Here's the plasma being formed over here. You're just seeing this maybe just 1 inch thickness of the liquid, and the grounded electrode is here present. And if you actually start the video, there's nothing present in it but salt, no PFOA and no other compounds. So you actually start, and you can see that the mixing is away from the plasma. This is just plasma-induced mixing, and there is a nice flow cell being formed over here, and this cell stays like this over time. So just plasma-induced mixing. So even if I just play this video longer, you were going to get the same results. However, if you put you've done the same experiment, but now you put 0.1 milligrams of PFOA, and you start the same experiment. Oh, I'm clicking something wrong. Okay, there is a reversal of the flow. Do you see that there is a strong inward flow cell that is actually being formed? And this is what we call a normal convective cell trying to fight this reverse flow cell. And actually, if you leave this for a long time, for minutes, the magnitude of this reverse flow is decreasing. And over time, and I think this video is so long, this will completely disappear, and normal flow away from the plasma will dominate again. So why is this happening? So the flow reversal actually occurs due to the concentration-driven Rangoni flow. So you have a plasma here, and you have a surfactant present in the liquid. Surfactant is degraded only in the plasma zone, and it's not degraded outside of the plasma zone. And you have a concentration gradient present in the liquid, which actually drives the flow in a different direction. So the flow is essentially reversed only when there is enough surfactant, whereas there is a strong gradient flow. When the surfactant is completely degraded, the flow essentially returns back to normal. So how does that relate to our experiments? Essentially, do not turn off the argon bubbling in the liquid, because we do not want for our system to have any concentration gradient-driven flow. We want to have the absolute complete mixing, which is achieved only with argon bubbling, right? Only then we can override the concentration gradient-driven flows. But it's an interesting problem. And I actually want to mention that if you don't have argon bubbling, we're actually conducting a huge study when we're actually showing when there is no external bubbling that the removal of the compound is directly proportional to the magnitude of the velocity mixing of the gas-liquid interface. So that's actually very, very interesting. So in the last part of my talk, I'm going to talk of the plasma treatment of very highly conductive solutions, essentially plasma treatment of brine. We are working with a company, ECT2. They're an ion exchange company. So this is the company that treats very high volume of low concentration PFAS groundwater. So what they do essentially, they treat hundreds of gallons of water contaminated with PFAS, and then every 2 weeks or so, they stop their system and they regenerate their resin with a proprietary mixture of methanol and high concentration of salt. So they clean up their resin. And what we are left with to treat are very small batches, small volumes of high concentration of salt, methanol, and huge concentrations of PFAS. Okay? The problem is we cannot use the current reactor setup even on the bench scale because of these two challenges. When the electrical conductivity is really, really large, you know that the plasma treatment area becomes very, very low. Actually becomes almost laser sharp, just goes into the one point. So treatment area is very important for effectiveness. We cannot have this reactor treating this type of compounds. And the second is we have excessive foaming. We bubble argon gas through a highly concentrated PFAS solution, and this thing foams like crazy, right? Due to the very large concentration of PFAS. So what we have done to overcome this problem, we have actually, again, worked around the properties of the compound, of the solution, and we have switched for our point-to-plane configuration. We had a point in the gas and plane in the liquid to a point-to-point discharge over here. So now we are essentially having a surface spark discharge, and we can actually increase or decrease the size of these two electrodes, and what's in the solution is completely irrelevant. We can have any kind of conductivity that we want. We have actually measured the removal rate constant and compared it for point-to-plane and point-to-point and got better removal for the point-to-point than for the point-to-plane system. So this is the system we're actually sticking with right now. We have since scaled up that system. You can see a small batch scale plasma treatment system where we have 6 pairs of electrodes. You can see they're point-to-point electrodes. They're all charged by individual set of capacitors. We had to modify the external network in order to get sufficient plasma to treat these compounds. And you can see maybe how the plasma actually, there are small plasma treatment areas within this reactor. We can actually, we treat an actual brine from a site coming from the ion exchange. We were able to remove the concentration of these compounds within a reasonable time frame, 30 minutes. Think that these are very high initial concentrations of PFOA and PFOS. And we are actually happy with these results because these guys regenerate their system every 2 weeks. So we have 2 weeks to treat very small batches of PFAS in the system. Looking what's happening at the high conductivity, we've noticed lots of peculiarities with a high conductivity solution. This is a problem not really well studied in the literature. Very few people look at the conductivities greater than maybe 1 millisiemens per centimeter. All of our drinking water is maybe 500 microsiemens per centimeter, but we've seen some lots of peculiarities. So we looked at the PFOA removal at different solution conductivities. So we started from 10 millisiemens to, this is maybe 40 and 60 millisiemens. And we saw that the removal of this compound increases with conductivity. But at the same time, energy per pulse is also increasing with conductivity. But we really wanted to know why there's an increase in the removal. What is the conductivity actually doing? What are the species responsible for the removal of these compounds at very high solution conductivities? So again, we didn't want to do all the analysis on the PFOA. So again, we compared the PFOA removal and rhodamine B removal as a function of solution conductivity and different electrolytes. And you can actually see that for PFOA removal, it doesn't really matter what's in the liquid, what type of salt do you have in the liquid. The removal increases with an increase in conductivity. However, for rhodamine B dye, you can see when the sodium chloride is used as a salt, the removal increases, but with sodium nitrate is used as an electrolyte, the removal actually stayed constant. And we originally thought that had something to do with aqueous electrons because sodium nitrate is a really well-known aqueous electron scavenger from radiation chemistry. But these results actually discouraged us from thinking that aqueous electrons have anything to do with these results. So we took, we really didn't know in which directions to go, so we went and performed some experiments on rhodamine B dye to explain results. So what we have done is we first wanted to investigate plasma-generated light on the removal of these compounds, because at very high solution conductivity, the emissivity, the plasma, is really, really bright. That's really known from the in-liquid plasmas. We have put the dye in a cuvette. So it was the quartz cuvette. And we were actually wanted to see the extent to which dye can be removed in the cuvette just from the light emitted from the spark plasma. So there are no other defects. And we put two different volumes, 1 milliliters and 10 milliliters of the dye in the solution. And we actually observed that at very low solution conductivity, you can actually remove the dye just from the light in the plasma, about 40% in 10 milliliters and about 83% in the 1 milliliter solution, which was really, really neat. But it was very interesting that the removal actually decreases with an increase in conductivity. And I've actually seen, I went to the experiments, the plasma with an increased conductivity becomes less bright, actually becomes really, really weak, which was really, really unusual at that point. So we actually at that point thought, and even now are thinking, that the fundamental chemical reactions when the electron collides with water molecules are different for different solution conductivities. So the reactions, the electron collision reactions with water, which we think are important at low conductivity, may not be valid at this point right now, and it could be some other other types of reaction that require higher electron energy taking place at higher solution conductivity. We have also measured the concentration of hydrogen peroxide in the bulk liquid. So hydrogen peroxide is an indirect measure of OH radicals in the liquid. And we have seen that no matter what electrolyte we have in the liquid, the production rate of the hydrogen peroxide decreases for all of the salts. And this is not due to the scavenging of the ions present in the solution. So chemistry is essentially weaker also with an increase in conductivity. If you just look at the UV part of the OES spectrum, you can see at 600 microsiemens there is still an OH band present. So there are OH radicals in the system, but at 60 millisiemens this completely disappears. So we really do not understand why. So looking back into the PFOA results, so PFOA is removed nicely regardless of what type of electrolyte you have in the solution. So we went back and go back to our MD simulations where we discovered that PFOA orients itself is entirely in the gas-liquid interface. So we assume that the PFOA degradation is primarily controlled by the gas phase chemistry. It doesn't matter what's in the liquid, okay? And we measure the surface tension, right, of the PFOA as a function of conductivity and saw that it's decreasing. So what that means that there is a salting out effect happening at very high conductivity, where with an increase in the bulk salt concentration, the molecules becoming essentially more hydrophobic and tends to go more to the gas-liquid interface, which explains why this compound would be degraded better at high solution conductivities. However, unfortunately for rhodamine B dye, this is not the case. For rhodamine B dye, the salting out effect plays no role. You look at the surface tension of the rhodamine B dye as a function of conductivity, it stays the same. So there is really nothing to explain the behavior of rhodamine B dye as a function of solution conductivity. However, this compound is lying almost flat at the gas-liquid interface with some portion of it exposed to the plasma. And we hypothesize that rhodamine B is primarily controlled by the liquid phase chemistry. That being said, we can explain why chlorine-based salts have an effect of the removal, but cannot explain why sodium nitrate has no effect on the removal. So I showed you earlier that with an increase in the concentration of chloride-based salt, the removal of the dye increased. And this is the last slide actually that I have, and a very interesting result. So look at this. This is the removal. Chloride salt, the removal actually remains unchanged as a function of conductivity. I have never seen anything like that. We do not know how to essentially explain this result. Why would the bivalent chlorine salt have no effect on the removal, but monovalent chloride salt would have an effect on removal. But we think it's an interesting fundamental research problem, and we are still working on figuring that one out. So just to summarize what I said, so we think that for the plasma-based treatment of different compounds, the extent to which a compound resembles a surfactant will be a determining factor whether your reactor is going to work or not. We know for a fact that plasma-based water treatment is now more effective than alternative treatment methods for PFAS removal. Bulk liquid transfer is something that cannot be neglected in studying interfacial dynamics. It plays a huge role. I showed you earlier the concentration-driven Marangoni flow, but also temperature-driven Marangoni flow could play a role as well, but we need to find a way to measure the interfacial temperatures. If you treat highly electrically conductive solutions, that's a whole new area of research, and everything we know about low conductivity solutions does not apply to high conductivity solutions. And I showed you the last slide. There is an unusual effect of the ions taking place in interfacial chemistry, and I think if we solve this problem, we will gain a better understanding of interfacial reactions. So I would like to thank my graduate students and my postdocs for contributing to this work. NSF funding for the fundamental investigations of the gas-liquid interface. These agencies, DoD agencies, for the PFAS work, as well as Air Force, Global Foundries, EPA, and DMEX Plasma for funding the plasma reactor scale-up. Thank you for your attention. Yes. Oh, sorry. That was
a great presentation. I really enjoyed that. Thank you. Do you see application for biologics or virals?
Yes. I have an ongoing project where we investigate decontamination of bacteria, let's say, in the liquid. And our results indicate, and the manuscript is now currently under review, that it's only the electric field that is contributing the most to the inactivation of bacteria. So it's very interesting because we've done gas-liquid discharges were ineffective essentially for the inactivation of bacteria in the liquid, but direct in-liquid discharges were. And those actually, the mechanism of those doesn't proceed via radical. It's really the electric field-induced electroporation on the side of the microorganism. So yes, it works, but the reactor has to be targeted, yes, for the particular microorganism. I hope that answers your question.
One of the configurations that you showed in the first slide, where you have, yes, I'm looking to these two hemispheres, looking like a spark gap. You see this?
Which one? What is it?
G. Yeah.
Glide arc.
And, you know, so how this works? So you apply high voltage.
There is
the toe, and then the gas flow. Is it going to generate a plasma or it will arc?
It's an arc.
It will arc.
Yes.
Okay. All right. This understood. My second question. Of course, I have seen that there is an improvement when you have a laminar flow with bubbling versus just laminar flow. Is there an optimization technique for the size of the bubble and the bubbly flow?
Yes. So yes, so there is. So we have done experiments, very crude types of experiments with trying different bubble sizes in our treatment system. The smaller the bubble size, the better essentially removal, because the surface area is essentially much larger. So we have custom-made diffusers from Norway being built for this reactor, because they can produce the finest bubble size that we actually need for this type of experiment. But yeah, the smaller bubbles, the better.
Last one. Do you have to stick to 60 hertz?
I don't have to stick to 60 hertz, but we have done parametric optimization. Energy efficiency goes down. You can increase the frequency, but the energy efficiency will go down. So 60 hertz is our optimal frequency.
Thank you.
You're welcome. Yes?
In your plasma reactor design, you said that the thickness of the water layer was about 1 inch. What limits that thickness?
What we want to have at the exit. Do you know what I mean? So we can have very large thickness, but the removal is not going to be good. So we want to have complete removal for the entire reactor volume. Does that make sense?
Removal of the pollutants?
Or removal of the pollutants. So when you get a steady state, you want to get the concentration be below 70 nanograms per liter. So if you decrease or increase the removal, you will not get that at the reactor exit.
So changing the thickness changes the removal rate?
Exactly. You just need, if you have a thicker a liquid layer, you just need to wait longer time. So you have to reduce the flow rate through the reactor to achieve the same thing.
And that's based on the surface area that the plasma penetrates through the water? Okay.
Yes.
Could it be possible that hydroxyl radicals are still important when, for example, if you generate a fluoroalkyl radical at that point, you know,
Yes.
you could get these unzipping type of reactions?
Yes.
So that maybe you have a combination of
So we are doing the DFT, density functional theory simulation. So we have calculated the rates of all different radicals with PFO and PFOS. The reaction still proceeds with hydroxyl radicals, only it's extremely slow. The second step is important. Once the radicals are formed by the electron attack or whatever other mechanism, OH radicals are essentially important in completing the chain propagation.
And then, if I may, so you have chloride in there. You looked at the fate of chloride.
We have.
What do you get?
So we produce the chlorate. I know your question is probably targeted at chlorate. We do produce chlorate, but they are way below what needs to be in the groundwater.
Any perchloride formation?
We don't have perchlorate formation.
Because with electrochemical,
I know.
you form that.
We specifically look for that. Yes.
Have you guys looked into around metastable densities potentially as a mechanism for degradation of the PFAS?
No, but we are waiting for you to help us with that. We do very little. We'll do very little plasma diagnostic, except for basic core. Yes, we do. We don't do any kind of spectroscopy and to calculate gas temperatures. But yeah.
So what's the launch association energy for the carbon chloride in PFAS?
I don't know from the top of my head. Is it? I really don't know.
Because you said that you think
15
PFAS
EV? No.
I think it's much higher.
Okay.
Yeah, I don't remember.
And sorry, and I have it in my paper.
PFAS degradation was due to gas-based chemistry, and that argon metastable energy lies above the dissociation energies. Might be partially responsible.
Yeah, that's true. I don't know from the top of my head. But we do have a discussion, yeah, in the paper on the possibility of the argon species, and we do compare the ionization rates in the paper. I just don't remember. Yeah, I can get back to you on that. Yes.
So when you show me the surfactant sticking out of the water, it's hydrophobic, so I guess it's just trying to get away from liquids.
Uh-huh.
Right? What effect does that? You're injecting charge into the surface, and so you're getting some interface simulations show you can get a charge gradient, and that some people call it like a double layer.
Mm-hmm.
In the surface. Does that influence is that accounted for in the models with how the stringy thing?
I know. We don't account for that. But we think the electric field plays a huge role in the orientation of this molecule. So these simulations were not done with the plasma. They're just gas, vacuum, liquid type simulations. But yeah, the charged layer 100% plays a role, and so is the electric field. But we have no way of measuring that at this point.
Okay.
Yes.
So similar to kind of bubbling the argon through the liquid, to be considered misting liquid through the plasma?
Yes, but it's hugely energy intensive. So it's a trade-off. That would be the best. If you can spray things through the plasma, that's the best way. But spraying is, you want to stay away from that.
Any other questions? Going once? Going twice?
Okay. Oh, wait, there's one more question. So the only time they can degrade is from the time they go into the reactor for the time to get outside of the reactor. Yes, because they're also hydrophobic. But it's not only PFBA. So this is C8 goes to C7, C6, C5, C4. So C4 is not very surface active, so it's highly likely plasma will not be very good for the removal of that compound. But C7 and C6, and I don't know if C5, they're still surface active. So they'll get bubbled with the argon to the interface, and they will get degraded. Okay. Think, Fishalina.
Wait. Okay, let's thank her.
Okay.
Any possibilities that we can also employ magnetic field?
Yes, there is. There is.
I didn't ask the question because I think this may be appropriate.
No, there